Now that we've introduced a new function, the exponential function, we need to understand that it has an inverse. So just as a quadratic is square, the inverse is a square root. Addition, subtraction pretty much undo each other. We've got to find what's going to undo an exponent. So that's the task today, is to find what undoes an exponent. So if I go look at a graph of the exponential, and if you recall, that's a J-curve. We know from the vertical line test this exponential is a function. Now, how do I tell if its inverse is a function? We use this line test, if you recall, and that is called the horizontal line test. And again, that's to determine if the inverse of an exponential is a function. And since the horizontal line test passed, then the inverse of this exponential function is a function itself. So how do we find this inverse? Well, if we look at exponential form, y equals b to the x. B is the base, x is the exponent. So notice it's an exponential form because my variable is in the exponent position. So to find an inverse, if you recall, we just switch my y and switch my x with the x and the y. So that's the inverse. But that's not really handy because y is what we want to solve for. So we have a way of writing this, and it's called logarithmic form. So if I want to convert this inverse, x equals b to the y, into log form, we write the word log for logarithm, we abbreviate it. My base is b. The logarithm is equal to the exponent, and this is the value. So when we set this up, it's kind of a back and forth move. If you remember, b to the y power is x. And so the logarithm is an exponential inverse, and that's how I undo exponentials. So a quick review of exponential properties before we start evaluating logs. If you recall, we add the exponents when we multiply. Here both a and b get the exponent because there's multiplication, and exponents are multiplication. When I have a power to a power, I get a to the power of m times the power of n. A to the m over b to the n. Again, it gets to both of them because division is on the same level as multiplication. In this situation, if you recall, you get a to the m minus n. And so what we need to remember then is when we have a negative exponent, it's equivalent to 1 over a to the m. It just tells you to flip it. We did a proof that showed anything to the 0 power is 1. And if I have a to the 1 over n, that's a fraction. For example, if I have a to the 1/2, that is the square root of a. So we need to make sure that we understand those, especially negatives and fractional powers, because those are going to come about, and then it gets confusing if you can't remember those rules. So let's evaluate some logs. When I look at this, I say log of 32 base 2. That's how we read that, log 32 base 2. What is this asking for? Well, I want you to simplify, make this statement smaller. In other words, what's the value? So to do that, we're going to just go ahead and set this up as an exponent. Okay, so my base is 2. I'm wondering what power on 2 is going to give me 32. So when I look at this, this is saying what exponent on 2 is equal to 32. That's the question being asked. So what exponent on 2 is equal to 32? That would be 5. Let's look at the next problem. What exponent on 8, what exponent on 8 gives me a 2? Uh-oh, I need to go backwards and down, and if you recall, that x is going to be 1/3. It's a 1/3 power, which says I'm taking the cubed root. The cubed root of 8 is 2. So my exponent then is equal to 1/3. So again, to get out of log form, just set it up into exponential form. We usually don't solve things in log form. We transfer it into a form we're familiar with. In this problem, it's saying what exponent on 3 is equal to -2? Well, what exponent on 3 is equal to -2? So if we're thinking about that, is there such an exponent that I know? Is there such an exponent that I can find? I can't. Don't make the mistake, well actually I can if I have a calculator, but don't make the mistake of saying this is not equal to 3 to the negative 2 power. This is not the exponent. What I'm looking for is the exponent, so be very careful on how you set that up. So to look at properties of logarithms before we look at their graphs, if I have the log base a and I'm looking for 1, in other words, what exponent on a gives me 1? That would be 0. Anything to the 0 power is equal to 1. The log of a base a, in other words, a to what power gives me a? That would be equal to 1. The next you have to do with that idea of an inverse. So I have the log of a to the x, base x. What's that going to be equal to? Whoops, I rewrote that here. The log of my base is a to the x. In other words, a to what power is a to the x? Well, if you look at this, since my bases match and they're equal, that just means the exponents have to match. So the answer to that would simply just be x. Now let's try the next one. And this one looks a little tricky. It's a to the log, and that's a power, of x base a. What is that going to be equal to? Well, if you think about what's going on here, we have f of x is a to the x, and the inverse of that we said was the log of this, which is rewritten. And if I merge those together, we know that if I compose f with f inverse in the other direction, I get a to the log of x base a, and because these are given to be inverses, we proved it already, I'm going to get x out. What I like to think is, because they're inverses, logs cancel exponents, and the resulting value is just a. Another way I could set it up is just saying a to what power equals log of x base a, and that would be x. So those are just some properties to be aware of. I don't know that you need to memorize those, but if you just reset them up as exponents and think of the idea of an inverse, they kind of come out for you. So that was the first lecture, just introducing logarithms. The next one is on the graphs of logs.